thank you for having me and for Chiara for the most well-researched introduction I've ever received. Yeah, that's right. So I'll be speaking about the prospects for gravitational wave background detection with Advanced LIGO and Virgo. And the focus of my talk today is going to be on detecting stochastic backgrounds with LIGO and Virgo. But this is a much broader field looking at stochastic backgrounds than just LIGO and Virgo. And there are very exciting developments that I won't be focusing on mostly here in other observational astronomy fields such as pulsar timing and cosmic microwave background measurements. That said, I've tried to make my talk as general as possible in order to highlight some of the exciting things, opportunities with LIGO in the near future, but make it as broadly applicable as possible. Part of the reason I wanted to focus on LIGO is just because I have a limited amount of time, but it's also a very timely thing to be talking about right now. On the right-hand side of this slide is a plot taken from the LIGO Livingston logbook, and this is showing how our detector sensitivity is improving as LIGO commissioners work very hard to improve it. And this is a spectrum of displacement, meters per hertz as a function of frequency, and the red curve right here is a sensitivity that was achieved back on December 1st, so about a week and a bit ago. And with this sensitivity, the next stage of Advanced LIGO with this level of commissioning can already achieve about 50 megaparsecs of reach for seeing compact binary coalescences. This is about a factor of 2 greater than we had with initial LIGO. And this is just the beginning of this era of advanced detectors, which will enable us to do some really exciting gravitational wave physics. And I will be talking about here what we can hope to do for stochastic backgrounds with advanced detectors. So before I begin, I wanted to give a working definition, a practical definition of what a stochastic background is. And there'll be 2 parts to this. The first is the little audio demonstration. The stochastic background is, I'm going to define here, as any signal which is created from a superposition of many separate sources. And the simplest way to demonstrate is with this little audio. So here, first I'm going to play a binary neutron star signal. And here I'm taking just the gravitational waves created from the last moments of a binary neutron star coalescence. This is converted into audio, since you can hear the frequencies that are associated with binary neutron star coalescence. And that just sounds like this. Now, if you imagine that all throughout the universe there are binary neutron stars coalescing all the time, and the rate of this is probably about 1 per 100 seconds or so, but bear with me and let's just pretend that the rate is much higher so that every second or less there's a binary neutron star coalescence. Then you would get a signal that sounded like this. This is sometimes called a pop-point signal or a non-Gaussian stochastic background. If you increase the rate still further, you get this, which just sounds like static. That's a Gaussian or a semi-Gaussian background. Now, 2 of these signals I just played for you are going to be signals that I'm going to call stochastic backgrounds today. And that's because of the definition that I'm proposing for this talk, and that I also think is the correct definition for the observational gravitational wave field. And that is a stochastic background from an observational standpoint is defined as any source composed of these many separate signals where each single source is not separately resolvable. So that is to say, you can't pick out the individual binary neutron star coalescences in that audio I just played. Now, in the case of the pop-point signal I played for you, you could probably hear individual binary neutron stars, but imagine I added some noise on top of that so that there was some static, some detector noise, and you couldn't hear them all. Then, by this definition, this would still be a stochastic background. It's formally, mathematically, if you talk just about the signal, maybe you can differentiate them. But in practice, if you can't, with your realistic detector, realistic noise, and realistic search algorithms, if you can't tell the difference between these separate signals, it's a stochastic signal from an observational standpoint. So that's my definition of stochastic. And this is in contrast with some definitions in the literature where we use a very formal definition involving Gaussianity or overlap of frequency time space. Furthermore, I'll be talking about not just the stochastic background, but multiple stochastic backgrounds. And that's because I want to be able to talk about the different sources of gravitational wave backgrounds that could have been created in the history of the universe. And we'll refer to these separately.
Eric, in that Gaussian video that you showed, is it what the detector hears? In the sense that did you multiply the signal by the inverse Fourier transform of the noise perspective?
So the question was, is the sound what the detector hears? And the answer I claim is yes, but I have not added noise. So
that's okay.
So there's no noise added, but the detector should be calibrated in a way that the frequency response is flat. So yes. Okay, so why is the stochastic background interesting? Why do we care about it? There we go. The stochastic background is interesting because it can tell us about all these different times in the history of the universe, starting from the present day and working backward. So this is a famous cartoon from the particle data group. We have the Big Bang on the right-hand side and the present day over here. And if we start at the most recent part of the universe, then the stochastic backgrounds that we look for from these times are from ordinary, in quotes, objects such as binary neutron star coalescences, like I just played for you. And I'll talk more about astrophysical sources like this later in the talk. These sources, we know they exist. We know that there's a stochastic background formed here because we know that they're binary neutron star systems. We know that they coalesce. We know to within a few orders of magnitude what the rate is. And so we know that somewhere in the vicinity of Advanced LIGO's eventual sensitivity, we will be in the ballpark, in the right area where we might be able to detect this. And if Advanced LIGO can't, it will be, the next generation will be there. And these are interesting, these sources, these stochastic backgrounds, because the contribution, the primary contributions to these astrophysical stochastic backgrounds, though it is in a recent nearby universe, compared to the other transient signals that LIGO will see, is coming from the most distant sources that LIGO will see. These are, the main contribution to astrophysical backgrounds is something that we would measure in redshift, like a redshift of 1 or 2. These are not hundreds of megaparsecs away, but truly distant objects contributing the bulk of this signal. And we can learn about their populations by studying these backgrounds. However, if we go back earlier into the universe, we can probe potentially even more exciting physics. For example, we can get gravitational wave backgrounds created from bursts from cosmic strings or from phase transitions in the early universe. These sources have much greater theoretical uncertainty because, for example, to stick with these two examples, we don't know that cosmic strings exist, and we don't know that there was a first-order phase transition in the early universe that would have occurred at such a time as to produce a gravitational wave signal detectable today by an experiment like LIGO in the right frequency band. However, by the flip side of that coin, we know that if we do detect cosmological gravitational waves from this earlier phase of the universe, we have the potential to learn very exciting new physics that we didn't know about ahead of time. And so this area is extremely interesting. Finally, if you go back to the very beginning, the period of inflation following the Big Bang, we get into more very exciting physics. This is a time in the universe with an energy scale of 10 to the 15 GeV, so this is physics that it's difficult to see how we could probe by any other means besides cosmology, and in particular gravitational wave cosmology. And this area has been in the news a lot recently because there's a claim by the BICEP2 collaboration of a detection of gravitational waves from this epoch, which is now subsequently in question as dissenters are claiming that this might be, in fact, entirely explainable due to dust. But while that controversy plays out, this remains a very exciting signal. We are pretty confident, like we know that there's an astrophysical background at some level in the recent universe, we're pretty sure that there is a signal from inflation because we have strong evidence that inflation occurred, and we know that inflation creates this amplification of vacuum fluctuations. So we strongly believe that there is this signal here that we will eventually be able to detect in gravitational wave cosmology.
Stochastic backgrounds are usually broadband. So we can combine many of the little quarter hertz bins in this green spectrum in order to constrain a power law. And let's pick a single power law with just flat energy density. If we pick a flat spectrum, we can move down to this green curve all the way down to this horizontal black line. And that represents our sensitivity at 1 sigma to a stochastic background. So this is in the realm of 10 to the minus 9, 2 times 10 to the minus 10. And now you can imagine repeating that for other spectral indices. So this is one choice of spectral index. This is the flat energy spectrum. But imagine you try some other spectral indices. So you draw some other lines, and these all represent the optimal combination of frequency bands. If you do that for many different slopes, you obtain a smooth curve, which is the locus of all of the power laws that you can constrain. This is a power law integrated curve with the reference that cut off at the bottom, but this is how I will be presenting sensitivity in the rest of the talk. And as you can see, there's a big drop between these two quantities, and so this, I think, is the best way in order to convey information about sensitivity of future searches and future limits when we obtain them. And the way you interpret this is as follows. If you have some spectrum, which is this, that represents some astrophysical model which you're trying to detect, if it doesn't intersect this blue line, you have no hope of measuring it with a signal to noise ratio greater than 1. If it does intersect this blue line, then you will have some signal to noise ratio greater than 1. So that's how you will be reading these plots as we go on. All right. Before I get into some of the different sources we're going to look for with Advanced LIGO, I wanted to take a slide and just talk about where we are with initial LIGO as we have just finished up our final analyses of the initial LIGO era and get ready for advanced detectors. So these are two different, very similar looking plots, but from two different papers. The one on the left is showing energy density limits as a function of frequency, and the LIGO results of these little ones up here for our most recent science run, which was S6, and then Virgo, the Virgo detectors of ESR 2 and 3. And this one was just published in Physical Review Letters. I'll come back to what it tells us in a second. This plot on this side is results back from all the way 2005-2007 run, which was called S5. And this, these results are for 2 co-located detectors at Hanford, which we no longer had during S6. So these give us a much better limit at high frequencies. I'll talk more about this in a moment. So at any rate, the upshot is that for these initial LIGO results, we observed no evidence of a signal, so we set upper limits. And you can see something of the power law integrated curve shape from these lines. And this is where we'll get down to for the advanced detector era. And here are some predictions for what we might see from astrophysical backgrounds from binary neutron stars, binary black holes, in realistic rates. So we're not there yet with initial LIGO, but we will be getting into that regime with advanced detectors. And there are some other models included on this plot as well. I wanted to mention briefly this nice result that just was accepted in the Physical Review P for H1, H2. These are our co-located detectors at Hanford. Here, what we're able to do is by using the fact that the two detectors are in the same place, we don't have this penalty factor from having non-co-located detectors, and we were able to improve on these results by a factor of 180. Unfortunately, our analysis was restricted into this higher frequency band of 460 to 1,000 hertz. We'd like to be able to work around 100 hertz, where the sweet spot of the detector is. And the reason we couldn't do that is because the two Hanford detectors during the 5th science run shared a common vacuum system and were subject to some common noise sources, such as acoustic noise, that coupled into both detectors. And this is the correlated noise I mentioned earlier in the talk that can limit our ability to do stochastic background analyses. So I'll come back to this once more later. But this should give you some idea of how you can lead by having co-located detectors, but also the dangers of correlated noise. All right, so I'll go on now and talk about different sources that we hope to be able to detect in the advanced LIGO era. So first, astrophysical backgrounds. My definition of astrophysical backgrounds, these are signals, stochastic signals that are created after the radiation-dominated era and include emission from ordinary objects, binary neutron stars, binary black holes, of the stellar mass variety, rotating neutron stars, the first stars, at lower frequencies, supermassive black hole binaries, and white dwarf binaries. and potentially more exotic mechanisms such as quantum strings. As I mentioned earlier, we know that these backgrounds exist, but the energy density spectrum is uncertain, and here's a plot showing that. This is, again, the energy density spectrum. The blue curve is that same power law integrated curve I showed earlier for you. And these two dashed brown lines represent two different models, two different scenarios, we'll call them, for what the astrophysical background from binary neutron stars might be like in the Advanced LIGO era. The lower dashed curve corresponds to a rate of CBC coalescences so that Advanced LIGO would detect 26 individual binary neutron star coalescences for every year of science data. Our nominal realistic rate is 40. If, on the other hand, the number of binary coalescences per year that we detected with Advanced LIGO, if the rate was more in the neighborhood of 260, which is easily possible given the uncertainties in astrophysical rate estimates, we would be up here. This signal is just out of reach of even a hint of detection after 1 year. It would take multiple years of integration at design sensitivity or something better than design sensitivity to see this. However, if the rate is a bit higher, we could have a dramatic detection of an astrophysical background in less than a year. I want to give one other example of an astrophysical background before I move on and talk about cosmological backgrounds. There are other astrophysical backgrounds, but I need to limit myself to avoid speaking too much about them. So the other one I wanted to talk about is the astrophysical background from neutron stars in our own Milky Way galaxy. And it's thought that there are something like 50,000 neutron stars in the Milky Way that emit gravitational waves in LIGO's band. And if you assume that all of those neutron stars have some average ellipticity associated with them and calculate the stochastic background, it turns out that looking for the stochastic sum of that signal is actually a pretty interesting exercise. And that's demonstrated on this plot. The y-axis is the ellipticity of the average neutron star in the galaxy. The x-axis is the number of neutron stars in the galaxy. And I don't know if you can see it, but there's a faint cyan dashed line right here, which corresponds to 50-something thousand, which is about what we think the number of in-band neutron stars is. And using our most recent data, our most recent results that I showed you for the two Hanford detectors, you can infer that since we didn't see any signal with that analysis, that the average neutron star ellipticity in the galaxy is about 10 to the minus 7 or less. And this is not as good of a constraint as we get from observing individual neutron stars that are nearby and are electromagnetically visible, so we can look for them with matched filtering. But it's no more than, say, a factor of 2 worse than that. So this is getting into a pretty interesting region. With Advanced LIGO, which is in red, using the Hanford-Livingston detectors, you can't really, at first glance, do a lot better than 10 to the minus 7 ellipticity. And that's because of this huge penalty we pay at high frequencies from the overlap reduction function. However, this plot is very conservative. It was created by assuming that the signal from Milky Way neutron stars is isotropic. And we know it won't be. We know it will be concentrated toward the center of the galaxy. If you imagine that we redid this first analysis with a more sophisticated analysis that looked for a directed search and looked for stochastic gravitational waves in a way that mimicked the expected density profile of the Milky Way, we could do better. And we don't know how much better we could do because we haven't done this yet. But we know that we can't do better than this, which is this black line. This corresponds to the sensitivity of a co-located pair of advanced detectors. So that represents the maximum you could do if you had like a point source at the center of the galaxy. But it's interesting to compare this and this, and we expect that the true sensitivity of such a directed search will be somewhere around here probably. And you can get down lower than we can get now with individual targeted searches for pulsars down to a few times 10 to the minus 8. Question, Albert?
Yes, for the 50,000 neutron star population, what did you assume about the spin distribution function?
This comes from a standard simulation package that incorporates, as I understand, the latest models of neutron star evolution. Regenbaugh was responsible for that part of this work. All right, so that was just a very brief overview of astrophysical backgrounds. So we'll talk a little bit about cosmological backgrounds now, which are backgrounds created in the earlier universe. Here's my working definition of cosmological backgrounds. So first of all, some examples. Cosmological backgrounds can be created from phase transitions, preheating, alternative cosmologies, and other models, at least a few. And the discussion I'm going to be showing you now is based on a recent paper that I did with Tom Giblin. And this paper is just an interesting story behind it. Tom was visiting Caltech a little over a year ago, and he made an offhand comment to me while we were walking around that advanced LIGO is unlikely to detect a cosmological background because, well, you know, stochastic cosmological backgrounds don't go above 10 to the minus 11. And I said, no, I was not aware of this. And I pressed him on it further, and the discussion turned into the following phrase. We sort of rephrased Tom's initial assertion as follows, that many cosmological predictions for stochastic backgrounds, many at least, fall below 10 to the minus 11. And there's a suite of common features to these models, common physics that sets the scale. And so in this paper that we did recently, we looked at what are the systematic common features to these models that obey this rule of thumb, and what is the physics behind it. So in what follows, I'm going to show the work in this paper, which is essentially a back-of-the-envelope calculation showing where this rule of thumb comes from. And we'll have a few assumptions. We're going to talk about cosmological backgrounds that are created after inflation and during the radiation-dominated epoch, so when the universe is less than 47,000 years old. We're going to assume that the length scale of the source is subhorizontal, so that the source is causal. And we're going to assume that the source is associated with a specific wave number, k star, which is to say that there's some time in the universe, history of the universe, when this source comes on, and then it's going to come off. So it has some temporal property to it. And everything I say is going to be not applicable to astrophysical backgrounds, because this is all contingent on this assumptions about the radiation of the era. And I'll spare you the full derivation, but just show you the hand-waving highlight rail. You began with this source-time-Gordon equation, where the strain perturbations that we're trying to measure on this side are sourced by this quantity S, which is the anisotropic stress tensor, stress energy tensor. And that in turn depends on T, which is the regular stress energy tensor. And we're going to assume this parameterized form of T. So we're going to assume that it's Gaussian peaked, and it has a peak value of k star, which is our characteristic scale for our Twine model. And then we're going to assume it has some width, sigma. Finally, we'll give it an amplitude A, but the amplitude is going to disappear in the final, it's not going to show up in the final calculation. So the real thing to focus on here is that we're going to assume it has some characteristic scale associated with it and some width. And then we're going to take this simple parameterized Twine model and turn the crank in order to see how the energy density spectrum from the source is related to the observed energy density spectrum today. When you do this, you obtain the following expression. And we have this is now the gravitational-wave energy density spectrum today. The 0 means today. And we have a prefactor and then several variables, which I'm going to go through now. The first variable is alpha. And alpha is just a fraction of the total energy density in the universe, which is available to the source. So the most it can be is 1, the least it can be is 0. If you have alpha equals 1, that means your all the energy density in the universe is acting as a source for your cosmological background. The next variable we have is beta. Beta is the ratio of the square of this anisotropic stress tensor to the stress energy tensor squared. And this is a measure of basically gravitational wave emission efficiency. How effective is your source at emitting quadrupolar radiation? Beta equals 0 means that it's a lousy emitter. Beta equals 1 means it's a very efficient emitter. Finally, we're going to assume an equation of state parameter of 1/3, which is pretty standard cosmology. And then there are also these two other factors here, k star and sigma, and then you have k star divided by the Hubble constant, Hubble scale. And much of this scaling is already noted in these previous works. If we then, so if we have this expression, our next goal is we want to say, let's make this peak of this energy density spectrum as high as possible, because we want to ask the question, what is the best advanced LIGO, the most optimistic scenario we can concoct for advanced LIGO and for other experiments? And so we're going to tune these parameters in a way that we think maximizes this energy density spectrum peak. Now, really, if you were being very careful, you would have to do this for individual models, because the different parameters that we're treating as free parameters are actually related to each other, and a given model predicts specific values of these different parameters. But our goal is something broader. We want to make generalizations. And in particular, we want to look at generalizations that are true for large classes of models that involve, for example, phase transitions and preheating, in order to understand trends. And to that end, we're going to plug in two fiducial values for this. So k star over h greater than 100 is, we're going to plug in k star over h is 100. And this is saying that you can't have more than 100 wavelengths within a Hubble volume, or within the Hubble distance. And this is something that comes out of numerical studies of phase transitions. It's difficult to get this to be much smaller because of causality. Similarly, sigma over k is chosen from the same numerical studies to be no smaller than 1/2, as this is the numerical value that's seen in many studies, which is the smallest you can make a process in the early universe before. It's enforcing the fact that a cosmological process has to have some weight associated with it. And if you plug in these fiducial values, if we're choosing to try to maximize this peak value, we get this expression. And now we're going to plug in different values for alpha and beta. And we're going to somewhat arbitrarily give these values names based on our reckoning of what we think is realistic, optimistic, and pessimistic. So alpha, remember, is the fraction of the total energy density in the universe that is available to the source. So it can definitely be no greater than 1, so we're going to call 1 optimistic. Realistic, 0.1, is a typical value from numerical simulations of things like phase transitions, and pessimistic is a not uncommon small value, 0.02. Beta, we're going to pick our three values for optimistic, realistic, and pessimistic by doing a little simulation, a little numerical study. We're going to pick 6 random phases that describe the anisotropic stress energy tensor and project out the anisotropic stress energy tensor and do this many times randomly. We get this distribution of beta. And the peak value, or the median value of this distribution, we're going to call the realistic value. And then we're going to take 1 sigma, 1 standard deviation on either side and call it optimistic and pessimistic. And beta, remember, is a measure of how efficient the source is at emitting gravitational waves. When you plug in these values of alpha and beta for optimistic, realistic, and pessimistic, you get the following results. And this is kind of a punchline. For the most optimistic case, and for these values that we've chosen, the peak value of energy density is 5 times 10 to the minus 10, realistic, about 10 to the minus 12, pessimistic, 10 to the minus 14. And this is roughly consistent with Tom's initial assertion that it's not easy to make a gravitational wave cosmological background with an amplitude much greater than 10 to the minus 11. As a next step, what we did is we compared the energy density level of these different predictions, which are shown here in blue for optimistic, green for realistic, and red for pessimistic, and which, by the way, don't depend on frequency. These are frequency independent. We apply these alongside some current and planned experiments. Advanced LIGO, these are, again, power law integrated sensitivity curves, once again. This is Advanced LIGO over here, which is just not quite getting to the top, not quite getting to the optimistic scenario. This is a hypothetical pulsar timing array, which is designed to be ambitious but feasible for the near future. And this is Einstein telescope. and this is the Big Bang observer. And pulsar timing gets below the realistic, or the optimistic level, but not yet to the realistic. Einstein telescope cuts into the realistic, but not the pessimistic, and you need the Big Bang observer to get a strong signal from all of these. And in each case, you need the frequency of the cosmological background to be such that it shows up in your detector band anyway. So even if the amplitude was optimistic, if it showed up at 100 hertz, you might miss it in something like Big Bang. There are some exceptions to this rule of thumb, and it's at any rate just a rule of thumb, not a hard upper limit. So in addition to that, signals that are frozen in during inflation, so things that happen during inflation as opposed to after inflation, can escape the rule of thumb because the energy scale argument that we make essentially doesn't apply. Additionally, if there's a non-standard equation of state in the early universe, you can avoid the rule of thumb, although to the best of my knowledge, there is not yet a compelling argument for why there would be a non-standard equation of state in the early universe. You can also evade it with massive gravitons. And then finally, cosmic strings and astrophysical sources that emit in the after the radiation-dominated era can also evade it. So my interpretation of the rule of thumb is that it's a simple way of understanding how scaling arguments explain why many of the models in the cosmological literature predict energy density spectra that peak at no higher than 10 to the minus 11, though some models do peak higher than that. And in particular, as an observer, which is my primary role, what I find most useful about this is that it's a way for me to assess a model. So if I see a prediction made of a cosmological background that peaks in Advanced LIGO's band with energy density of 10 to the minus 8, then the way I see this as being most useful is I can ask, what is it about this model that allows for Advanced LIGO to have such a good chance of seeing it? Is it something that happens prior to inflation, and therefore escapes the rule of thumb, or is it tuned in such a way that it has alpha equals 1, beta equals 1? And I have a little anecdote to support this. After the paper appeared on the archive, I was contacted by an author of a paper about stochastic backgrounds from the decay of cue-ball condensates. This was not a cosmological background that I was familiar with, well-versed in, but I was able to go through the paper and find all of the parameters that can be plugged into the rule of thumb. And doing that, a consistent picture was able to emerge from me of what was happening in this paper and how to reconcile it with advanced LIGO sensitivity. Okay. Jonah, please cut me off after this slide or whenever, depending on how long you can talk. All right. So that's my little bit about cosmological backgrounds. Now I want to ask and answer a question that we get a lot in the LIGO stochastic community about, well, suppose you actually see something, you get a stochastic signal. You're talking about astrophysical backgrounds, you're talking about cosmological backgrounds. How will you know what you're actually seeing? How can you ever be sure that you're seeing a phase transition, for example? Really, all you're seeing is excess coherence into detectors, right? This is a good question, but we've been working very hard in the past few years to develop answers to it. I won't go through them all in detail now, but I'll just mention them. So one thing we can do is we can look at the anisotropy of the signal. And this is a way, for example, to know if we have a source, like I mentioned, Milky Way, neutron stars. This would be something that we would see clear signature of anisotropy. And this is an example of one such study we did, published by the LIGO and Virgo collaborations, which is an upper limit map of gravitational-wave power from different points in the sky. In this case, there's no signal present, but if we saw a signal that had the shape of the galactic plane, we would know that that was astrophysical in nature. Another thing that we've been working on is using other measurements of gravitational waves in order to construct energy budgets. So, for example, let's suppose that Advanced LIGO detects 40 binary neutron star events after 1 year of science data. And let's suppose that we measure the energy density of the stochastic background to be 10 to the minus 8. those two numbers don't quite add up, because if you take 40 binary neutron star coalescences and you plug it into a cosmological model, you say, well, we see 40 in the nearby universe. How many should we see in the entire universe? There are some theoretical uncertainties, but what you would find is that it's hard. There's tension in that. It's hard to account for 10 to the minus 8 energy density if you're only seeing 40 local binary neutron star coalescences. And this is the way that you can begin to construct an excess energy density argument where you can say that your knowledge of the local universe plus your understanding of cosmology can be used to subtract off or at least create some budget for what you expect to be there, and then ask, do I see anything above and beyond that? We also can look at the spectral fit of the signals, as well as test the Gaussianity of the signal, and that is to tell the difference. These are pipelines that are in the process of being developed that can maybe eventually help us distinguish between this case, which is more likely to be astrophysical, in this case, which can be astrophysical, but could also be cosmological. And how should I wrap things up now? Okay, so I'm going to skip over. So I had some slides on correlated noise, which are very fun, but I'm going to skip over them because I think I've gone over. So here are my conclusions. The stochastic background and measurements of the stochastic background by LIGO are a powerful probe of the history of the universe. And LIGO and Virgo may be able to detect an astrophysical background, for example, from compact binary coalescences. And the binary neutron star case is especially promising. Frankly, a cosmological detection by LIGO and Virgo would be a little bit of a surprise, given the energetic arguments. Although not impossible, there are ways around it, and it would be very exciting to saw such a signal. Finally, there are ongoing efforts to mitigate correlated noise, which is something I skipped over, but which is a threat to our measurements and our ability to carry out these searches, and I can talk about in Q&A if anyone's interested. And with that, I want to thank you, and also thank Alan and LIGO Lab for all my time at Caltech and my LIGO Lab. It's truly been a pleasure to be working here. Thanks.
Given you mentioned a stochastic background from CBC, is it much more likely that it will actually just be single resolvable cases in the case of the atomic detectors?
Oh yes, by a lot. So 80 individual binary neutron stars will be detected in order for us to detect a cosmological bound. So there'll be a huge, if you count that as one signal with a Poisson error of 80, that'll be huge compared to the stochastic signal. But they're different sources. Stochastic ones come from much further away, through probing a different population of objects that have at redshift, really. So I see them as complementary.
Given that the cosmological background might be really low, in the foreseeable future, is it only be more kind of signal that we can rely on to detect, or do you think there are other ways we don't really?
Is the question, is there anything we can do beyond what we're already doing to find cosmological signals? I haven't thought of anything yet. So astrophysical signals, let's see if we can go back here, we can play games with. The fact that they might be in this popcorn regime and design algorithms that can pull that out of the data more efficiently than we can now. And realistically, I think that would be a very big victory if we could gain a factor of 2 in energy density, maybe that way. But it would still probably wouldn't be orders of, I would be shocked if it was orders of magnitude. A Gaussian signal, our pipeline and the math that underpins it is optimal. It can't be improved anymore. So you have to find something about cosmological backgrounds that we've overlooked, unfortunately. All right.
So you told that interesting story about some archive paper where it's a larger signal than you expected. Did you find that there was actually a flaw in it then?
Not a flaw, but I'll have an extra slide on this. All right. here are the two assumptions. This is saying that k star over h is going to be on a scale of 100. This is some number that I'm remembering is less than 1. And then here, this is the statement about the width. And these are almost precisely the fiducial values that we chose. And the number that the authors quoted in the paper was, I think, 10 to the minus 8 in energy density. And I'll go back here and we'll look at where that is on the rule of thumb. Now, shall I go here? So if we plug in 1, 1, and a third, you get about 10 to the minus 8. But that's now telling you that you have the entire universe as a source, and that it is every possible, it's almost 100% efficient at emitting gravitational waves. That's already something that is useful to me. And in the body of the manuscript, it describes how numerical studies have not yet produced the level predicted by their analytical calculations. So, and I don't think it said exactly what those were. So I took that to mean that, you know, and this is only a superficial reading, but it allowed me to say, okay, well, this can work out, but it would require large values of alpha and beta, and if the numerical studies aren't supporting 10 to the minus 8 yet, maybe the numerical values are not giving them alpha equals 1 and beta equals 1. And if I was really wanting to question more, I could contact the authors and say, hey, are you getting unity for these two variables, and is that reasonable?
I think that just about brings us to the end of the hour. The thing our speakers